We're going to spend this week talking about standard collections, including our good friend the vector, but I think before that, another warm-up is in order. So what I want to talk about is a use of vectors to represent 2D arrays. Now we recall that obviously we've been using all semester vectors to replace the C-style arrays that we used in 111. Now C++ actually does support C-style arrays, hence why I'm referring to them as C-style arrays. We are allowed to write something like this if we want to. But why would we want to? When we have a vector, why would we need the old-fashioned C-style array, which has caused us all that grief over time? As you remember from 111, all of the things that they can't do, versus vectors, which know their own size, can grow and shrink as needed, and still give you all the benefits you're used to with arrays, so being able to index them easily, for example. And so if we want to represent two-dimensional arrays, we want to find some way of doing so with a vector. Well, let's see. A vector is a one-dimensional array, or it's the analog of a one-dimensional array we've been using in this course. So I suppose if, just like how in C, the two-dimensional arrays that we work with formally are just arrays of arrays, I suppose then that our two-dimensional arrays in C++ will be vectors of vectors. And so we can create that. Here I'm creating a vector called t, whose elements are also themselves vectors. And the initializer for t, I've split it across multiple lines. The initializer for t consists of 3 vector initializers. And using the normal interpretation that we use of what a two-dimensional array is, dating back to CSC 111, we'll interpret each of these vectors inside the larger vector to be one row of a table, of some two-dimensional table. So the first thing I want to do is demonstrate that this is valid. We've already seen, and I've mentioned this repeatedly, that I can make a vector of whatever type I want. So as long as I can create a type and store it somewhere, I can make a vector of it. And so it's quite valid to make a vector of vectors. And so here I've got a vector whose elements each are individual vectors of int. And as the comment above is pointing out, this is actually quite a bit more flexible than the 2D arrays that we're used to, because we know that a vector can have an arbitrary size. And so nothing is stopping us from making, for example, one row shorter than the others. Nor is there any reason why we wouldn't necessarily modify a row after the fact. So I could start off with a table that's 3 rows and 5 columns and discover later that I've modified one row to have 6 columns. But for now, let's just assume that that's our business. So if we're the programmers, we should take care to not do that if we would rather that all the rows have the same size. This actually sort of ties into that issue I raised last week of if we have particular ambitions for what a type is supposed to represent, can we prevent any unauthorized or unexpected use of that type? So outside of the normal restrictions we would impose. That is something we will address, but later in the course. For now, though, I can create a vector of vectors, and I can treat it just like I would any other vector. And I want to demonstrate that I can use these as functional 2D arrays. So the first thing is I want to print out the table using for each loops. I guess I should begin by compiling and running what I have. Doesn't do much. So I want to just print this table out in 2 different ways, just to demonstrate the indexing strategy. The first thing I could do is if I want to print the table out with 1 row per line, well, each row of the table is one element of the outer vector. So I've got my vector of vectors, and each vector inside is a one-dimensional array that represents a single row. So I suppose if I want to iterate over it, I could try something like this. For each row in T, and of course the element type of T is vector of int, which means row will be a vector of int, although I guess maybe I want to use these by reference to avoid making any unnecessary copies. For each row in T, well, I guess what I'll do is I'll illuminate what I'm going to try here a bit further. So print the values in the row with a space after each value, and then when I'm done, print a new line. Okay, so the first thing I'll do is print the values in each row. So for each value in the row, and I don't see a reason to use a reference for this because making a copy of a single value isn't really a big deal. For each value in the row, I'm going to print the value out. So I'll do stdcout, and then I'll print v, and then a space. And then at the end of the row, I will print a new line. We can try that, and we can verify that it does indeed print every row on a line by itself. Of course, it doesn't line the elements up nicely. So of course we are getting every element of every row, but maybe we'd like it if we could format them to be lined up column for column. That's more of an I/O thing, so that's a question of how our output is generated. Something that's really annoying in C++ and something we can do if we need to, but for today, mostly I care about the fact that we can work with this two-dimensional array. So I'm going to live with this irritating looking output because it is valid output. And then the question is, can we print this table out using traditional indexing? So using the indexing scheme we would be used to in, for example, C for two-dimensional arrays. So we'll use indices I and j to refer to rows and columns respectively. So in this case, the number of rows is the number of these smaller vectors inside the larger vector t. So in other words, obviously, if each of the elements of t is a row, then the size of t is the number of rows. So I'll say I is less than t dot size, I plus plus. And then I want to do something very similar. I want to print each row out followed by a new line. So I'm going to just cannibalize that statement printing the new line, and then I'll loop over the contents of each row. So here what I'm going to do is I'm going to use an index j to keep track of where I am in the row, which column I'm working with. And then the question is, how big is the row that I'm on? Now, to be very flexible, I want to make sure I don't assume every row has the same size. And so how big is the row that I'm working with? Well, I guess if I'm working with row I, well, row I would be the element I of the larger vector. So t dot at I. The element type of t is vector, so t dot at I will be a vector of int. So I'll ask that row, what is your size? And then I will iterate up to that. And so I've got my value j iterates over all the columns in the current row. And so then if I want to print out a particular value, I'll go t dot at I. That gets me into row I. And row I is a vector, so I have to then do dot at j to get into column j. And then I'll print a space. All right, and there are two different ways of printing out this two-dimensional array I've constructed as a vector of vectors. One of them leveraging this for each loop, which allows us to sort of ignore indices and just print the values out. But a second one using indices, not only because we can do that, but also because there are lots of cases with a two-dimensional array where you need to use indices, and it's good to see at least one loop that does that. One common observation people make is that this looks really ugly and weird, that having to do t.at seems a bit bizarre. Now, I don't think so. I actually think that this is sort of congruent in my mind with the way you use square brackets on a 2D array in C. But if it does bother you, there is a way around it, although I don't know whether it's going to be any better. What you could do is you could use a reference variable, keeping in mind that references, as we described a couple of weeks ago, references are just a way of giving a new name to an existing thing. What I could do is I could go pull aside the row that I'm working with and then give it a name, so the name row. I don't even have to bother with its type, even though I know its type is vector of int. And then I could work with the row directly using that reference. And we find that often when you notice your notation's getting a bit too dense, using a reference variable gives you an easy out. It gives you a way of attaching a name of your own to some complicated sub-expression that you find yourself using over and over again. And so that's also an option. Although to be honest, I think it does make the code look a bit cleaner here. I actually sort of like the nested indices because it makes it more obvious to me that I'm working with a two-dimensional vector of vectors. Okay, so we've seen that that's possible. Maybe now we agree that we can use vectors to represent the equivalent of a two-dimensional array. That actually wasn't the real reason I brought this up. I think it's a good exercise, but I actually had an ulterior motive, which is suppose I want to write a program that uses these tables of values over and over again. We're constantly throwing around vectors of vectors. And we can stare at that and say, we're pretty much hitting our limit for notation that we want to see. This is a pretty ugly looking type. And unfortunately in this course, it's going to get worse. We're going to work with a lot of types that are pretty hideous, even this week. And so std vector of int is something I don't want to have to keep writing out. There's got to be a better way. So it turns out, just like in C, we have options for making up our own new type names that refer to existing types, including things like weird compound types. And it's a directive called using. And so in this version of the code, so it's the same code as before, in this version of the code, I have created my own type called table. And I've defined it to be a vector of vectors. And so that means if I ever try and create a variable of type table, then I just use type table, and it's initialized exactly as a vector of vectors would be. So the using directive is a C++ idiom that allows you to define your own types. It is similar to the word typedef in C. Now it turns out C++ also supports typedef. And there are times when, in fact, it is useful. In our context, we will try and use the using directive everywhere that it's possible. In general, most of the common uses of typedef in C are superseded by using in C++. And then we have this, I guess I left that in, left in some debugging code. We have the code that we had before, basically, which iterates over my table, and I just want to write that in to prove that we can still use that with this using directive. And notice that the type we use is just table and not vector of vectors, because the using directive defines for us a new name for it. And there it is. So we're able to print the table out even though it's of type table. Of course, we can still use it as if it were a vector of vectors because deep down it actually is. And in fact, there are lots of other places in the language where types have been suspiciously renamed. You noticed in a video from last week that we were using variables of type std_string. But at one point, the compiler revealed to us that it knows that std_string isn't the real name of this type. I believe at the time I made some kind of reference to Russian literature or something. The type std_string is actually essentially a using directive over top of a far more complicated and hideous looking type name. And so the using directive has lots of different uses. And to be honest, even this, I still have an ulterior motive. Even this isn't the true point of this video, although we will find ourselves with using directives all through this course that we use to simplify type names. In fact, it's actually to try and get at this point, something that many of you have probably been wondering about since you watched the very first video, or like the first day of class, which is, why is it that I keep insisting on writing out the names of standard library features in full? std vector, std::cout, std::: invalid argument. I've alluded to that in the past, that there is a way around having to do that, and you might have noticed I seem to do a lot of extra typing because I insist on writing it out std vector. Many of you that have already looked for advice on Google or something probably have noticed that there is a way of using a shortened name for standard library features. And now in this video, I will grudgingly acknowledge what that is. So it is actually another use case of the using directive. So what I have in this file is actually that average grades exercise that we pretty much beat to death last week. We tried that in every possible way, but I'm insisting on resurrecting it for one last use, which is, here's a program that uses vectors all over the place. So I've got a vector being passed in as an argument. I've got a bunch of vectors in main, and we've worked with a lot of vectors already in this course. And you'll notice I'm not writing std::: vector anymore. Now I'm just writing vector. I've brought in the name vector sort of like a local name, which I guess can save me a little bit of typing. And you'll find that although I have this option, I don't really take advantage of it very often. I actually prefer to do more typing. And so the using directive, if you just say using and then give the name of a type, so for example, std::: vector, the using directive interprets this to mean you want to bring the type from wherever you got it from, so the std namespace, which is where all the standard library stuff is kept. You want to bring that type into the local namespace. You just want to use the word vector for it. So I'll compile this. We can see it does compile. And this allows me to use vector by itself, not std::. So if I want, I can choose to bring in parts of the standard library piecemeal to use them directly as local names if I'm sick of having to write std::: before everything. I could do the same thing if I don't want to write invalid argument. I could write instead just throw invalid argument. I guess I do have to write invalid argument. If I don't want to write std::: before it, I could use a using directive to bring it in, to import it into the current namespace. And then I just write invalid argument. And that's completely valid. It's completely valid to use using directives when you want to bring in types or anything else from the standard library to use in a local sense. Now, a couple of other notes, though. So first, I actually don't like this. I did not, it took me quite a while to convert to the way I currently do things. So currently, as you've seen, I like writing std::. Over the years, I have found this is actually very helpful. It makes my code more readable to me. I don't actually know what's in the standard library. The standard library is absolutely massive. Even I do not know everything that is in it. And so having a visual cue when I'm using standard library features is really helpful. It's also possible that there are things in the standard library that use names I might want to use myself. For example, maybe I want to make a variable one day called invalid argument. I don't know why I would do that, but I might. And using the name like this makes it hard for me to know, is invalid argument a type I made up, or is it a type I've dragged in from the standard library? And so it's hard to know, and therefore I sort of like having to write std:::. However, it is quite valid and it is good style to bring in individual pieces of the standard library using this notation. Because anybody wondering, hey, what is vector supposed to mean? They can go to the top of your file and say, oh, I see, you're using a using directive, so vector actually means std vector. They have a way of figuring out, of solving that mystery, of figuring it out. So that's valid. Although I still prefer to just write std::. I think the extra typing is well worth the investment. There is one other thing, though, and there is a version of using that is frowned upon these days. If you go look at an old C++ book or a new C++ book that is secretly an old C++ book in disguise, and I mean, textbook companies, I'm looking at you. So as many of you know, textbook companies are really very fond of taking ancient publications, moving some sections around, changing some formatting, and then calling it a new edition and charging you $300 for it. And they often do this without regard to how things have changed in the meantime. Publishing companies, now that I'm saying this on the internet, they might not do this anymore, but they often send me free copies of textbooks. And I have found that of the pile of C++ books I have received over the years, very few of them that have been published since, let's say, 2017 actually seem to reflect modern C++ practice. They seem to be very, poorly recycled old C++ books with a couple of minor changes. Now, those of you that know me in person know I complain about textbook companies all the time, so I'll cut that out. Come to the office hours if you want to hear me complain more about this stuff. If you read an old C++ book, or you talk to people that write old C++, you will see that they really like writing this directive at the beginning of their programs. Using namespace std. What this directive is saying is, go find the namespace std, which is where we keep all the standard library functions. So when I write std::, you can sort of view this : notation as a way of filing a bunch of stuff into a folder. So std is the name of a folder, a directory, and I've got a bunch of stuff inside of it. It's a convenient way of filing away all of the standard library stuff. This directive is saying, go into that folder and just dump it right out. Take everything in the standard library and bring it in. All the stuff I've brought in with my include directives, bring it into the local namespace so I can just use it directly. If I use that, I can then use every standard library feature without std::. I'm going to see if I can find all of them. We do use a lot of them and we don't even notice it. You'll notice a lot of older C++ programs do this. They use using namespace std and then just drag in every standard library feature as if it's something you created. Notice that without std::, it's hard to know exactly where this variable came from or this type or anything else. So I'll compile this to prove that it works, and it does. And that is a syntactically correct application of our using directive, but I think that it's nasty. And modern C++ practice has turned against this for a lot of different reasons. The biggest one is what I mentioned earlier. The standard library is huge. There is a ton of stuff that you're bringing in with this directive that you have never heard of before. When you say, go get the standard library, go get everything I brought in with these includes, and just turn it upside down and dump it on the floor, there are a lot of things besides vector and invalid argument that you are bringing in that you may not know about. And those names are now available and you can use them. So even if you use one by accident, you are now using it. I think that's a mess. I would much rather only bring in the names that I actually want, or even better, explicitly say when I'm getting something out of the standard library. And yet, this is a valid directive, although its use is discouraged. I would consider it to be bad style in the modern C++ idiom. And you'll especially notice things like this. So cout and endl. I've just now used them directly without std::. After all the time I've spent writing std::, this looks just off. There's something about this just looks wrong to me, which I think is a good thing, because what if I wanted to name a variable cout? Well, now I can't because the name is already in use. Think of all the other names that I've brought in from the standard library that I've never heard of before with this directive. And that's one reason why, although yes, you can bring in the entire standard library, I think it's a really bad idea. I think instead, if you really want to use a shortened name for something, like say vector instead of std vector, just put a using directive. You can then add using directives for all the different things you really want to use a shorthand for. So if I want to use all of the different features of the standard library that I see in the program, without saying std::, I suppose I'm welcome to just write all of these using directives. And yes, that's extra typing, but I think the trade-off of the extra readability and maintainability you get from this is well worth it. Although, as I said, from my current point of view, I think it's much easier to just, use std:::. But this is valid, and I think it's a good practice compared to the using namespace std thing, although it's a bit bizarre that you'd need to do this, because if somebody's wondering, hey, what's invalid argument supposed to mean? Hey, wait a minute, what do you mean indel? They can scroll up here and they can see you've sort of signed that waiver. You've actually indicated explicitly, no, I want the one from the standard library. On the other hand, using namespace std is a habit that I think it's best to get out of, because it results in code that can actually contain some hidden errors when you're using a standard library feature you didn't know existed. And it also makes it less easy for somebody glancing at your code to know where you're using your stuff and where you're using the standard library.